being punctual. This is a good sign. Punctuality is the soul of business. Mr. Ayotune, you have the floor.
All right. Good morning, everyone. I trust we are all doing great. It's good to have you and your team. Thank you for showing up in today's meeting. I expect us to have an exciting time and a futuristic conversation this morning. So, my name is Ayofasai. I'm the Director General of the African Space Foundation. I have members of my team here, Oluwaruntimi Bukola, with our international liaison officer. We have Samuel on also online. Both will be working hand in hand, with all of the students to be able to check the knowledge enhancement level in relation to the Project Dawn, which is the 3U CubeSat satellites we want to launch to space. So we're expecting an exciting time. I don't know if everyone has introduced themselves, but we can go ahead into our presentation, which will be handled by Bukola Oluwarantimi. Dr. Femi, I want to confirm, has everyone introduced themselves already?
No, I think we need to do that very quickly. So let us run through that. Let's start with the members of Africa Space Foundation.
All right, Bukola, you can go ahead.
All right, thank you very much. Good afternoon, everyone. I'm Oluwarantimi Bukola. I'm the International Liaison Officer of Africa Space Foundation, and it's very lovely to be here. I look forward to interacting more with you guys. Thank you.
All right, Samuel, you can go ahead.
Good morning, everyone. I'm Samuel Gwende, and I'm an aerospace engineer. I'm the Space Education Officer for Africa Space Foundation. I think that should suffice. Thank you.
All right, Dr. Femi, I think we're good from our side.
Okay, good. So everyone from OAU, please get yourself familiar with these faces from Africa Space Foundation. Get to know their names. They are going to be your direct point of contact in terms of the capacity building. Mr. Ayotune Fasnoya will be your go-to man when it comes to the resources that you need for the project.
Thank you, Dr. Femi. It's an exciting one. We are also excited to work with you, young people, and your passion and creativity, to be able to bring out the goal and objective of Project D.A.W.N as a whole, as a project team. Thank you.
The purpose of this call today is not just to kickstart the conversation, but also to understand where your knowledge presently is in terms of the satellite subsystems, and also to understand the resources available at your university currently. So I think that will lead to your presentation, where each subsystems will talk about what they know already about the nanosatellite subsystem, and you will then present the current facilities at your hand in your university. I understand maybe you have very little or nothing, but please tell us what you have. Your faculty mentor, Dr. Shiyi Fatoyimbo, or Latoyimbo rather, he has pledged full support. And also we have a new faculty member. She has joined the faculty. Now we have more hands to support you. Having said that, let's not waste time. Let us dive into your presentation.
I'll be sharing my screen now, and the sub-leads will take over with the presentation from there.
Okay, good. Go ahead.
All right. Good morning, everyone. My name is Margaret Bella Omunagwe, and I am the team lead for Structure and Mechanism Subsystem. So I'll be walking us through this presentation. So basically, our team is responsible for making sure that the CubeSat physically survives everything from the moment that it's built all the way to operating in orbit. So some of our responsibilities cover these 5 areas that I've highlighted here. Firstly, we are in charge of designing and developing the structural frame of the satellite to meet the 3U CubeSat standards. We also took note of the recommended standards, which I will talk about when we are going into our tasks. This basically means that we're in charge of designing the entire body of the CubeSats. Secondly, we're in charge of selecting materials. We're looking at factors like mass, how they respond to extreme temperatures in space, looking at their strength to withstand violent shaking during launch, and their overall workability to ensure that we can actually work with these materials that are selected for use. So thirdly, we're looking at computer-aided design. We're going to model all the structures. Basically, we want to make use of SolidWorks for this to create a full digital version of the structure of all that we're going to build. Next, we're going to ensure that the structure stays strong and intact. And how we're going to do this is by running analysis, and we're also by also staying in close coordination with other subsystems so that we'll not go or we'll all be on the same pace while working together. Next, we see the importance of documentation. So we're going to keep thorough documentation so that when a project is being carried out like this, no one will have to start from scratch, but you just have to follow process, and it makes things much easier. So we outlined the skills that our team requires, computer-aided design using SolidWorks. So then we're also going to use simulation basically to test our designs virtually, and using finite element analysis to let us see exactly where the stress is concentrated under real loading conditions. Next slide, please. All right, so I outlined two major tasks here: design and modeling, and analysis and documentation. So under design and modeling, our first big task will be to build a complete 3U chassis CAD model. It gives to give us a sense of scale. We're looking at a 10 by 10 by 34 centimeters, which was recommended in the Project D.A.W.N slides. Also, if we're trying to like view that, it's kind of like a large water bottle, like just to imagine. Also, we're looking at weight between 4 to 5 kilograms, and we're working with two aluminum alloys, 60616 and 7075T6, and both of which are, by research, they are widely trusted aerospace. They are widely trusted in aerospace applications. Also, we're looking at a structure of either a monocoque or a skeleton structure, meaning that it's either going to be a shell-based design where the outer skin carries the load, or a frame-based design with internal rails and panels. Yes. So next, we're going to be looking at solar array deployment and mechanisms, and the antenna deployment and mechanisms. Basically, we know that once the solar, satellite is released into orbit, it needs power immediately to actually run. So the solar panels will basically be folded flat against the body of the satellite during launch to save space and also protect them from vibration while going into orbit. So one thing that we need to understand that we are taking into consideration is that when this satellite is in space, there's really no second chance. So we understand that we're responsible for designing the entire folding and release system, which you definitely work on. Also, for the antenna, the satellite needs to communicate with ground stations back on Earth, which is the plan, and that's where the antenna comes in. So just like the solar panel, we're also going to fold the antenna, which will also be released while in orbit. So we're thinking of using a spring or bond wire release system for that. All right, so we'll round up our task. Last thing, I'm going to look at analysis and documentation. We're going to run structural stress analysis to verify that our design actually will hold up when it is launched. Then, like I said before, we're ensuring that we maintain up-to-date design documentation and create step-by-step assembly procedures to ensure that, okay, it can be easily followed through while in use again. So yeah, that's basically an overview of what the STR team is responsible for. Thank you very much.
I have feedbacks, corrections, but because of time, I'm not going to be stopping you guys. So I would like all of you to go through the presentation, and I'll provide all the feedback in a separate email to everyone. Okay? Is that okay with everybody?
Yes, looking forward to that, sir. Thank you very
Okay,
much.
okay, beautiful. So let's have the next subsystem, please.
All right, thank you, sir.
I
I
have
want to welcome you on board as your faculty anchor and direct mentor. I have a team of other colleagues that are going to work with me in training you and guiding you in this laudable project. And I believe it's going to be a smooth ride for us. At the end of the day, we'll look back and we'll be very happy to be part of this great team. Thank you for joining this call. And I hope at the end of the day, you will have career fulfillment as pioneer students to build our own indigenous, customized 3U CubeSat from this part of the world. Thank you very much, every one of you.
Thank you very much, sir. We are very happy that you are committed to this project. We really appreciate you making up time despite your busy schedule, and we wish you safe journey all the time you travel, sir. Daniel and all the team members, please, as you've heard from Dr. Sheyi, feel free to meet him, organize a meeting with him, ask him question, is readily available to support you. There are other members of the faculty as well from UN Actacy. We are onboarding them currently. So they are also your official support. We hope everything goes on smoothly. Thank you so much, sir. We'll get back to the presentation. So who is the next presenter for the command and data handling system? Please share your screen. Let us see what you have.
Good afternoon.
So
Okay, let's move to the next subsystem, please.
Good afternoon. Can you hear me?
Yes, I can.
Yes, we can.
Thank you for the confirmation. The EPS is the electrical power systems and is basically the aspect responsible for generating power and storing power that the system will rely on during eclipse phases and the rest of the phases, the rest of the mode and everything. Basically, our responsibilities are to manage and maintain the satellite's master power budget. We are to come up with a budget that will serve the satellite and power every single component for however the satellite will last us. Interface and negotiate continuously with other subsystems to allocate power safely and avoid system brownouts. Yes, because we are going to be supplying power to other areas of the other subsystems. We need to be able to communicate with them and determine how much power they will need and how much power we can generate so that we avoid a brownout, a situation whereby power runs out and then systems fail. We are also to ensure the EPS design meets the strict 3U CubeSat launch providers safety requirements, especially regarding battery protections and physical launch inhibits. So we have to make sure that we follow the guidelines provided and make sure the satellite does not turn on before it is needed. Yes, because we are to make sure that we protect our battery to avoid things like overcharging or try as much as possible to limit the usage of battery to avoid excessive drain if possible. Then we have to keep proper documentation of design progress and power margins. The previous sub-things are said, documentation is very, very important. Skills required, systems architecture and power budgeting. We work with the STR, figure out the architecture of the system, and then plan the power budget that is going to run the whole system. entertain communication and negotiation, which is very important because every sub-team is going to need power to run whatever design they come up with. So we have to be able to communicate with them and provide the power necessary for them to function. Basic circuit design and PCB routing concepts. This is basically the wiring of the whole system, ensuring power gets to the systems as efficiently as they can. And component evaluation, determine if we can get something like the idea of power saving components that are also as efficient but consume less power. Next slide, please. All right, so our tasks, we are to build and manage a comprehensive power budget spreadsheet detailing power generation versus power draw. We are going to be generating power through solar panels. Then we will compare it with the power that is going to be drawn by other subsystems. So we are going to compare it and see how efficient we can make the system. Because if you have our power draw being greater than power generation, then there's a problem. There has to be some adjustments. And we're also going to determine the solar array configuration, body mounted versus deployable, based on the 3U chassis size of 10 by 10 by 34 centimeter. We're going to be working closely with the STR to make sure we have the perfect configuration for the solar panels, if they are going to be body mounted or if they are going to fold and then be deployable. Calculate battery capacity requirements based on the standard low Earth orbit eclipse times. So there is a particular time when the Earth blocks the sun. So for that moment, we will not be able to generate any power through solar. So the system actually has to be able to function throughout that period of time without failing. So we're going to have to calculate the battery capacity requirements and work towards that. Design goals: reliability, maintain a strict 20% power margin on all calculations to account for space environment variables. So most of the materials function differently in space. And so we're going to have to work with a 20% power margin, just in case materials function differently in space. So we are going to have to calculate that and give a margin for that change. Efficiency: utilize maximum power points tracking, MPPT, to maximize solar panel output and ensure high efficiency power distribution. So we're going to regulate and control to sequence the absolute most effective way for solar panels and satellites as they tumble and change temperature, because we are dealing with materials here and materials change based on conditions like temperature. So we're going to have to calculate the changes that will occur and then work towards making the system efficient even when those changes occur. Then safety and thermal: ensure proper thermal management, heaters for the lithium-ion battery to prevent charging failures in extreme cold. Like I said in the previous point, our materials will function differently in space. So the fact that they work in Earth doesn't mean that they'll function the same way in space. So we're going to have to make calculations to account for that change. Thank you very much.
I think that was a very good presentation from the EPS subsystem. I think you guys are pretty much ready. I'm very proud of you. Let's go to the next subsystem, communications, please.
Good morning. Okay, good afternoon, sorry. So can I confirm if I'm being heard?
Yes, we can hear you.
Yes, I can hear you.
Okay, thank you. So the team lead for the comms subsystem is currently not available, so I'll be taking his place to present this. So to introduce myself again, my name is Toby Adebi, and here we have the comms subsystem overview. The comms subsystem acts as the mouth and ears of the satellites, managing data acquisition for transmission. So for this, basically, we describe comms as the mouth and ears of satellites because technically it's like the primary interface between the space segment and the ground segment, as it manages how data is packaged, encoded, transmitted, received, decoded, and passed to the onboard systems. So it's not just a system that's for passing signals. It's responsible for ensuring that the communication in the satellite is reliable and efficient under whatever constraints that might be present. For the responsibilities here, enabling reliable two-way communication between the CubeSat and the ground stations. So the first responsibility in establishing reliable bidirectional communication is more of designing a system that can maintain link integrity. I mean, despite the signal attenuation, because there are certain constraints that might happen due to satellite motion and environmental noise. So if there is reliability here, it includes not just proper connection, but also error handling and signal recovery, which allows for consistent data delivery as well. And onto the second here, acts as the primary interface for data exchange within the D.A.W.N constellation. Yes. Rather than just acting as a point-to-point transmitter, like transmitting information from just one point to another, we are treating this satellite the comms subsystem. We are treating the satellite as like a node in a distributed system, kind of. So it's capable of exchanging data across multiple endpoints. So and this will help to support scalability as well, and it would help build this wider data infrastructure than just doing this isolated mission. So there's this communication between all these different nodes, rather than this node is acting as independently, but it's more of a web, more of a like distributed system, exchanging data across this endpoint. On to the next, maintaining stable communication links during short orbital passes, typically 10 minute windows. I'm not, according to the knowledge that I have as of this point, I believe we'll be operating in low Earth orbit. So yes, communication windows would be limited. And so because of this, the comms subsystem for the satellite has to be optimized for this fast link acquisition kind of, and for efficient data transfer as well, because this is one of the constraints that would be working with, which in this case is like a tight time constraint because of just this 10 minutes window per ground pass. So every second that we can use to communicate has to be maximized, and it has to be very efficient. We can't afford to waste a minute not getting the proper data that we need from the satellites back to the ground. The next, managing high-speed data exchange and store and forward operations with other project roles. In comms subsystem, the data that we get is kind of stored on board and transmitted later after the availability of a link. So the reason for this is for data relay, in the sense that it ensures continuity of mission operations, and it allows the satellite to continue collecting data even when it's not in contact with a ground station at all. So it's more of, like I said, it's mutually exclusive. Is that the right word? Sorry about that. The next and the last responsibility that we have on here is collaborating with EPS for power budgeting and STR for antenna deployment. Okay. Transmission basically requires this significant power in the satellite kind of. So we are kind of going to be coupling comms with other subsystems, in the sense that we are coordinating with the electrical power system, which is the EPS, to ensure that whatever operations that the comms is carrying out or the satellite is carrying out is staying within energy budgets as well. And as for STR, antenna deployment and position, it kind of depends on the structural subsystem, right? So if the antenna is like, if it fails to align properly according to how we want it, communication performance can like be severely affected or degraded. So I feel like I know that comms is tightly coupled with other subsystems, and we don't need that. Sorry, okay. Sorry, yeah. For the design goals, ensuring high accuracy and precision in the my screen. Okay, ensuring high accuracy and precision in the TT&C, the telemetry tracking, and the command link. Well, for com subsystem, we're expected to prioritize like high accuracy in this in TT&C, telemetry tracking and command, because of this the higher the efficiency of this accuracy is how we monitor the satellite's health and control its behavior, because any error in telemetry could like lead to incorrect system assessment, and like any error in the command could result in doing certain operations that were not intended. So it all just goes back to the responsibility of the comms, whereby we need to establish a reliable two-way communication, because precision and reliability here are like very, very critical, and those are one of the things that we have to make sure that the comms subsystem is taken care of to ensure proper efficiency of the whole satellite operation and all. Supporting the functional IoT payload for remote data collection across Africa. Basically, this just comes to like undo multiple data inputs efficiently, same as when I previously mentioned about distribution or across different endpoints. So because from this different nodes, there'll be varying data loads as well. So, but it's the goal for designing an efficient comms subsystem is ensuring that the subsystem is handling this multiple inputs efficiently, is ensuring reliable transmission regardless of the difference in connectivity across these geographical areas and stuff. It's more of a proper support for the payload as well. Now, on to the tasks. Developing an SDR-based network link for flexible frequency management. SDR is a software-defined radio architecture. So the reason why we're having an SDR-based architecture would be more of, it provides like flexibility at the software level, and since like physical modifications are like impossible basically after launch, SDR still allows this changes whereby you can kind of like adjust frequencies, you can do some modulation schemes, you can change like communication protocols, and also it's making the system more like adaptable to like unforeseen challenges that were not taken care of before the final launching of the satellite and all, or the final project and all. The next task, defining the dual band approach using UHF, VHF for command, and SRX band. Well, basically, in a nutshell, that just means we are using like a dual band frequency strategy, right? So by using that to separate functionality. So as UHF, VHF is kind of like used for this low data rate, but it's like highly reliable command and control. And the SRX band, I think it's used for high data rate payload transmission as well. So this separation, this dual band is just ensuring that, okay, even if like high speed communication is like disrupted, we can still maintain control over the satellite. And this is one thing I believe is very critical for mission safety, because regardless any glitch or any flaw that's supposed to happen, there's supposed to be like this kind of, let's say, contingency that's supposed to fix that glitch, fix that flaw instantly without actually disrupting the whole system. So that's one reason why I'll be using this dual band strategy as well. But the next, designing and modeling the physical antenna and radio system to fit within 3U structural constraints. Um, the design of the antenna. Before I continue about this, the design of the antenna generally is already like constrained by the small size of the CubeSat. Sorry, am I still heard? Because sorry, can you confirm if I'm still being heard? Because it's showing me at work.
We can
Yeah, we
hear
can
you.
hear
Please
you.
go ahead.
Okay. Thank you so much. So the antenna design like is already constrained by the small size of the CubeSat, the 3U CubeSat. So I believe it's something that because of this, we have to like optimize it for compactness in the sense that the signals that can be received is like efficient and all. So because even small inefficiencies can like significantly like impact communication performance. So antenna design is also like one task that the comms subsystem is going to be taken very seriously in based on what I have. So the next task, the next task here that I have is developing and documenting the TT&C protocols for command. Well, developing structured communication protocols for that in the sense that the commands are like correctly interpreted and executed in the first place, whereby communication protocols are being developed rather to ensure that the data is transmitted in this format whereby it's error resistant. Would I say that error resistant here in the sense that the communication remains organized, it remains reliable, and it is essential and it is still efficient for maintaining the system integrity during the operations as well. And yeah, the next, why is my screen now? Let me just go to the picture here. Okay, so I think that's all for the tasks. And for here, the skills required. Okay, yeah, the skills required basically this is just showing what skills are required for every member in the comms subsystem actually, because as it reflects this interdisciplinary like nature of the subsystem, so we need like programming skills, the C++ and all for the embedded systems, the protocol implementation as well. The MATLAB is used for this simulation and verification, and particularly like in link budget analysis. I didn't mention that before because link budget analysis would be like needed to verify this communication feasibility. So as it involves like calculating transmitted power, like path losses, all these antenna gains, to ensure that okay, signals transmitted can still be like from far distances can still be received with sufficient strength and clarity and all. And also another RF fundamentals are essential for like understanding signal behavior as well. So yeah, in summary, I mean, the communication system is not just like responsible for transmitting data. I mean, it ensures that the satellite remains connected, it's controllable, it's operationally relevant, it integrates with every other subsystem, and basically it ultimately determines whether like the mission can be successfully monitored. That's to be validated from the ground because it's more of okay, we can't go there, we can't go up there outside Earth to check what's going on. So we have to ensure that we are getting the right information about what is going on up there from down here. So yeah, thank you. Hello?
Great job. Thank you. Is that all? Is there anyone else?
We have active determination and control system.
Is there any presentation for any other subsystem?
Yes, there is someone waiting to present ADCS. Please go on. You have the floor. Who is
Please go ahead.
presenting ADCS?
Hi, good afternoon, everyone. I'm Jesse Tony. I'm the technical lead for Attitude Determination and Control System, ADCS, for the 3U CubeSat nanosatellites. So An overview of the subsystem is that the ADCS acts as the eyes and the steering wheel of the satellite, and the system is responsible for figuring out exactly which way the satellite is facing in space and where it is moving so that it points in the right direction. And what is the responsibility of this sub-team? Yeah, our first responsibility is to find the direction by using sensors to figure out where the satellite is compared to the Earth and the Sun. And another responsibility is to, am I being heard, please? Hello, okay. So another responsibility of this subsystem.
We can hear you. Go on.
Okay, another responsibility of this sub-team is that it helps the satellite to stay steady in space. So staying steady, stop the satellite from spinning out of control while it floats in space. Yes, by using gyroscopes and other resources that we may have to make sure that the satellite remains in the what English will I use now? In the orientation is supposed to be. All right. And our responsibility is that to make the satellite point accurately. Yeah, to make sure that the antenna is perfectly aimed at the Earth so that it can receive and send signals, messages accurately. And also, the attitude determination and control system will also track the path of the satellite. We follow the satellite route as they travel around the planet. All right, so what are the skills we'll be needing in this system now, this ADCS? All right, basic computer coding like Python and C++. Yeah, to understand how the objects move and orbit in space, and knowing how simple space sensors and small motors work. Yes, we are determining the attitude of the satellite and to control how it works, how it moves, what it sees, where it is located. Next slide, please. Next slide, please. All right, so what are the tasks? Number one, we'll be setting up the sensors. We put together the sound sensors and digital compasses to tell where exactly the satellite is, and we control the movement of the satellite too. Just as I said, the ADCS is like the eyes and the steering wheel of the system. So we control the movement of the satellite. We use magnetic device and spinning wheels to gently rotate and stabilize the satellite. Also, we write the rules. This is just like writing the codes, the algorithm in which the satellite will operate on, and takes information from sensors and use it to steer the satellite. And use to steer the satellite. We write the lines of code needed to, probably to move to the right, to move to the left, for the satellite to adjust and steer the satellite. So what are the design goals? Number one, the link reliability as recommended from the Project D.A.W.N management plan. So we'll keep the spacecraft pointed within 2 degrees to maintain high-speed data transmission over X-band radio links. Just talking about maintaining that degree for a quality network link, so that at least there will be an assurance that the network link is aligned properly and that it's not out of control, yes. And also the mission redundancy, one of our design goals is to make sure that we validate all control algorithms through FlatSat, that's a flat satellite avionics testbed, and breadboarding and engineering model testing before flight, like before the flight of the satellite, yes. We will make sure we validate all the control algorithms by using these models, that's the flat site and the engineering model, and also the environmental resilience too. We ensure that the sensors and actuators are flight qualified to survive vibrations and thermal vacuum. That's the TVAC testing phases. Yes, those are our design goals in the ADCS. Thank you.
Thank you, Mr. Daniel. Thank you, Dr. Femi. Thank you, everyone. Thank you, Dr. Shea. It's been a wonderful time having everyone on board, and we are so excited to get to work. The core concept of what we're trying to do is to be able to pioneer space science and technology in Africa as a whole. You being the pioneer cohort makes it makes it a very good foundation. So we're expecting many more. Bring in your creativity. Like Dr. Femi has said, the team is on ground to support you. We have young guys who are exceptional, who can work with you. Next time we meet, have a lovely day, everyone.